All right, so for today's class, I posted a PowerPoint to Blackboard last night to help us kind of like follow along. And to start class, make sure you have this standard normal table out. Um, it's located under the week 9 tab. It's the standard normal table. We're going to use it to start class. And then also here's the PowerPoint I'm going to use. And then how many people have their graphing calculator, with them today, either the TI-83 or the TI-84? Anybody have? All right. Definitely keep this handy. So what I'm going to start class with today is we're going to do a couple more problems by hand that we were doing at the end of last class, and then I'm going to show you how to do it with your graphing calculator so that it's even easier. Okay, so that way you can just use your graphing calculator going forward. All right. All right, so let me just get a few announcements out of the way. So just a reminder, there's no class next Tuesday, the 3rd. It's election day, go vote, okay? I actually dropped off my ballot, so I don't know if people are voting in person or not, but go vote if you haven't, or drop off your ballot. It's really important. Homework number 4 is due next Tuesday. So if you go into the classroom under homeworks, homework number 4 is posted here. I highly encourage you, like right after class today, to go and just do homework number 4. It's actually it's on the shorter side. It's only 2 questions. And if you pay attention in class today, at least for the first hour, you'll be able to bang out this homework very, 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 very quickly. I promise you. Also, I've been talking about this for a while, but I'm going to move your next exam and homework number 5. It's going to be moved to Tuesday the 17th. It was originally scheduled for Thursday the 12th. I just want to give us an extra day to, get all the concepts down and review, because I think, the last exam, the scores weren't too great. So I want to just, get a review day in so everybody can get a really good exam score. Okay. Does that sound like an okay plan?
Yes.
I hope so. Thank you. Yes. All right. You're welcome. My goal is to have everyone get 100 on the next exam. Okay. So before I get started, does anybody have any questions for me about any of this? Did anybody look at homework number 4 yet, just out of curiosity? I don't know how to, 1C, let me take a look. So the between, is that the question you had, how you do the between ones? So don't stress too much about that. That was the question in the chat, right? Like having trouble with 1C. Yeah, so what you'd have to do is you have to look up the area for this value and then subtract away, look up the area for this one. I'm gonna do a bunch of examples of this in class today, probably at least 2, so that you'll see. And then if at the end of the class it still doesn't make sense, Danielle, then just post in the chat that, hey, Matt, end class, let's go over this one more time. Does that sound okay? All right, good. Okay.
Professor.
Yeah.
Just for this question, the student asked, that one is the one you have to go back and look at the normal distribution, the bell shape.
Yeah. Yep. Both of the problems. Yeah.
Okay.
So I'm going to do one more example by hand, and then I'm going to move in and I'll show you how to use your calculator. Okay. So any other questions before I jump into it? All right. I love this example. Have you guys heard of these things called Chips Ahoy's chocolate chip cookies? You guys heard of these things? Right? Like they were like a staple of my childhood. Okay. But they used to have, never in my life, okay. They used to have this ad campaign. And so I was born in the 80s, early 80s, raised in the 90s. So they used to have this ad campaign. And you probably don't, I don't know if anybody in here remembers it. I don't know how old everyone is, but they used to make this claim for every 18-ounce bag of chocolate chips, Chips Ahoy cookies, they used to say that there were 1,000 chips in every bag. Okay, I'm just curious. Does anyone ever remember that slogan or that ad campaign? So here's the thing: they used to make that claim, so they don't anymore. And so what they claimed is, look, you buy this bag, you're getting 1,000 little chocolate chips in your bag. And so it was like this amazing claim. Okay. So it turns out that there was this study done out of the U.S. Air Force Academy, and what they did was that they were like, all right, let's like make sure this is true or not. Okay. So let me read you the problem. The number of chocolate chips in an 18-ounce bag of Chips Ahoy chocolate chip cookies is approximately normally distributed. Okay, so what we're saying here is the number of chips in each bag is normally distributed. Okay, so that tells you it's going to be a bell curve problem. So now let me ask you this. Do you think every bag has exactly the same number of chips in it? Yeah, like no. Okay, it's a manufacturing process, right? So not every bag is going to have the exact same number of chips, but what they tell you right here is they give you the mean. Oh, let me go back, sorry. They give you the mean. So on average, there were 1,262 chips in each bag. That's pretty good. And a standard deviation, sigma, of 118 chips. Okay, that's just some information that gives you right off the bat. And this was a study done by the cadets at the U.S. Air Force Academy. And so basically what happened was the instructors like legit told the cadets you have to open up the bags and count the number of chips in it. So only at one of the U.S. military academies would that work. But anyway, so here's the problem. Suppose a bag of 18-ounce Chips Ahoy cookies is selected at random and the number of chocolate chips in the bag is recorded. Okay, so I'm going to select a bag at random. So I don't know how many chips will be in that bag. Okay, so I'm going to define that by the random variable x. All right, and it's just going to be the number of chips in the randomly selected bag. Okay. All right, so everybody okay if I go on? I've only got 2 questions for this section here. Okay. I'll wait, no problem. I have the noisiest chair. You guys hear my chair every time I move in it? Like make those big creaking noises? I'm sorry. I should probably buy a new one for Christmas or something. Yeah, I've had this chair this chair's old. All right, Liliana, are you okay if I move on? Okay. All right, so here are the 2 problems that I have with this, okay? What is the probability the number of chocolate chips in the bag is greater than 1,300? So you get like a super bag, okay? So this right here, this is an application problem. Okay, did I give you a 4-step process for solving this last class? Okay, yeah, all right. So step 1, the first thing you're going to do is you're going to define the variable. We already did that. Okay, so that was done on the previous slide, and we're going to write the probability statement. Okay, so I want to find the probability that it's greater, that the number of chips in those bag X is greater than 1,300. Okay, that's the goal. That's what I want to find. All right, does anybody remember what step 2 was? Sketch. Yep, perfect. Trust me on this, please, please just draw the curve, okay? So what we're doing here is we're drawing the distribution of chips in a bag. Okay, so we know that the distribution is normally distributed, okay? The high point of the graph is the average. And I'm sorry, how many chips did I say were in a bag on average? Was it 1262, thank you. Thanks, thank you. And I want to be greater than 1,300. So 1,300 is over here. Am I going to shade to the left or to the right here? If I want to be greater than. Yep, thanks. Okay, so it's a tail area to the right. So after we do that, step 3, does anybody remember what we do next? We have to compute something. Yep. Okay, so I only need to do one z-score here for this, okay? So the z-score is the x variable that you're interested in, which is 1,300 minus the mean divided by the standard deviation. So it's 1,300 minus 1,262. And I think the standard deviation was 118. Yeah. So let's grab our trusty calculator that never lets you down. I know this is going to seem silly, but this is a common mistake I see. All right. If you're going to plug this in your calculator, you have to put the top in parentheses. So it's 1,300 minus 1,262. Like it seems silly, but every once in a while I see this error on an exam. So just remember to put it in parentheses. And you get this number here, if anybody did it on their calculator?
Yes.
Okay. Thanks. So you have to round this to 2 decimal places, okay? The reason is we're going to go to our z-score table here, and all z-scores are to 2 decimal places. So I'm going to round it to 2. So this is 0.32. Okay, boom. And then finally, step 4. Step 4 is you just rewrite the probability statement and use the z-score table. So the probability that x is greater than 1,300 just now becomes, hey, well, okay, what's the probability that a z-score is greater than this number you just found? Does anybody remember how you find an area to the right, a tail area to the right here? Yep, you got, thank you. Awesome. I love it in the chat there. I got 1 minus, then 1 minus whatever. Yeah, you use the complement rule. So it's 1 minus, so I've got to go look up this z-score. So it's a positive z-score, so I go to the positive side. So you look up the first 2 digits is 0.3, which is right here. And then the last digit is a 2, so you go find 2 at the top, which is up here. So do you guys see that they intersect at 0.6255? Does everybody else see that? All right, so it's just 1 minus this, 1 minus 0.6255. So I believe that becomes 0.3745. Did I do that correctly in my head? Nice, nice. Math teacher does simple math. It's always a good sign. So whenever you do the whenever it's a tail to the right, okay, you see how it's shaded to the right here? Leonardo, yep. Whenever it's an area to the right, you always do 1 minus the table, because the table gives the area to the left. So to find the area to the right, you got to do the complement rule, 1 minus.
So basically, any problem that is greater than that of x.
Yep.
Okay.
Always, always. If you're going to do it by hand, when I would get to the calculator next, I'm going to simplify everything for you. Okay. All right. So if you remember, I started this problem by saying, hey, you know, what's the probability that there's, you know, or the advertisement campaign, excuse me, was that there's 1,000 chips in every bag. Well, now let's just compute the probability that the number of chocolate chips in a bag is less than 1,000. So you go to the grocery store, you buy this Chips Ahoy cookies, and there's less than 1,000 chips, okay? So it's the same problem, basically, okay? You're gonna write the probability statement. Now I wanna find the probability that X, the number of chips in the bag, is less than 1,000, okay? Step 2, what do I say is always the most important thing you should do? I know it seems silly, but sketch it, sketch it. So you're centered at 1262. And I want to be less than 1,000. So 1,000 is over here. I'm going to shade whoosh, to the left. So now it's an tail area to the left. How many z-scores do I need to compute here? Just one, just for 1,000. Okay. So the z-score formula is x minus the mean divided by the standard deviation, which is 1,000 minus 1262 divided by the standard deviation for chips in a bag, which is 118. So in parentheses, 1,000 minus 1262 divided by 118. Do y'all get this if you did this in your calculators? Okay, so it's minus 2.222. So the final step, my probability that the number of chips is less than 1,000 is the same thing as the probability that a z-score is less than minus 2.22. So it's a tail area to the left here, which is awesome. So that means we can just read it right off the table. So minus 2.22. Do you get 0.0132? Does anybody else get that? Yep, thank you. So another way to interpret this, what this means is roughly 1.32% of bags have less than 1,000 chips. So was their claim, question mark there? What did you mean by that? And the last, so what I'm doing, I'm just changing the probability to a percentage there as another way of interpreting it. Alyssa, did you have a question or no? No problem. No problem.
Professor, I do have a question. Where did you get the 0.0132 from?
Yep, so I get it from this table here. So I looked up the z-score of negative 2.22. So negative, so the first two digits are negative 2.2. And then the last digit is a 2 up here. So negative 0.22 where they intersect. Do you see it now? Yay, nay?
I do, thank you.
No problem. So to go back to this problem, remember I said they said there was 1,000 chips in every bag. Is that true? Like, no, it's not true, right? Because we see here that there's, you know, over 1% of bags don't have chips. And yes, Danielle, to answer your question there, whenever it's a tail area to the right, you do 1 minus. Whenever it's a tail area to the left, you just read it right off the table. All right. Not too bad. Think you could handle. So you don't have to sketch the problem. So what I sketch the problem to do is so that I know exactly what I'm looking at. Like the sketch tells me, oh, it's an area to the right. So I know to do 1 minus. Oh, it's an area to the left. I can just read it right off the table. So the sketch is just a crutch to help you solve it. Yeah, if you don't need the sketch, you don't have to do the sketch. I like doing the sketch. I probably should have been an artist or something, but like I just do the sketch. Okay. All right, so you are more than welcome to do this by hand, okay? Is everybody okay if I move on for a second then? Okay. What I want to show you next is how to do this using your TI calculator, okay? So it's a little bit easier on the TI-84 versus the TI-83 calculator. How many people just in the chat have a TI-83? You could just, I don't know how many people will actually respond, but how many people have a TI-83? Okay, a couple people. That's okay. You know what? So that's all right. So I'm going to show you how to do it both ways. Okay, I'm going to show you. Let's stop for a second. How many people have a TI-84 calculator? Okay. All right. So I'll be honest with you. TI-84 is a little bit easier. Okay. But TI-83, you know, it'll do the same thing. Okay. So I'm going to show you, I'm going to show everybody how to do it. I'll load up both calculators, TI-83, TI-84. Boom, boom, boom. All right. So your option to do this, here's the TI-83 and here's the TI-84. Everybody can see them both on my calculator, on my screen. I have no idea what a TI-80,000 is, or 8,000 is. Okay, it sounds like a Terminator. Okay, we're not gonna, I think you're trolling me, Leonardo.
Yeah.
Yeah, all right. Stop being a troll. Let's focus on stats. Okay. All right. So you see this button on your calculator called DISTR here. Okay. Everybody hits second function DISTR. Second function DISTR and second function DISTR. All right. Do you see the first two options called normal PDF and then the second one is called normal CDF? Can I just get a couple of yeses in the chats that you see it?
Yeah. Yes.
Okay, great. So we are never going to use normal PDF. So we've learned what a PDF is, right? It stands for a probability density function. The option we're going to use going forward is CDF. What this stands for is cumulative density function, okay? So if you scroll down to it on the TI-83, this is what makes it a little hard on the TI-83. is it just says normal CDF and then it tells you to input everything. On the TI-84, it asks for it tells you to put in the 4 commands. Okay, so on the TI-84, you see something called lower, upper, and then mu and sigma. Okay, the TI-83, it doesn't tell you that, you just have to remember it. But we're gonna do so many of these problems that on the TI-83, it'll just become second nature, okay? All right, so leave these up as it is, okay? So the command that you're gonna use is this normal CDF, okay? I'm just gonna put note, never use normal PDF in this class. Okay, always the normal CDF. So there's 4 commands. It has a lower value, an upper, and then you put a mean and the standard deviation in, okay? So the mean is gonna be the mean value mu for the variable, and the standard deviation is gonna be whatever sigma is, okay? These will be given to you, okay, in the problem. All right, the lower and upper are the only things that are a little weird, okay? And after you see me do 2 examples, it's actually like a piece of cake what the lower and the upper are, okay? So you guys ready to do an example and see how easy it is for your calculator to solve these for you? Okay. I highly recommend, and please listen to me on this one, I highly recommend using your calculator going forward, okay? You are more than welcome to do this stuff by hand, okay? But your calculator just takes a problem and does it in 5 seconds for you, okay? All right. So here's the first example, all right? I think I have 2 examples. I have one about pregnancies and then the one about the weight of cement, okay? I think you actually have, if you looked at your homework, there's a problem very similar to weight of cement here. Actually, I think it's the same problem. I just changed the numbers, okay? So, you know, you guys know I had a kid, and of course, you guys will hear him in about 10 minutes when he wakes up from his nap, for which I am always eternally sorry for. But so this is actually real information. I found this quite interesting. So the length of human pregnancies is approximately normally distributed, okay? So, you know, if you think about it, right, not every child is born exactly 9 months, right? So my kid came a little late, but it follows a normal distribution, and it tells you the mean is 266 days, and it tells you the standard deviation is 16 days, okay? So now what I'm gonna do is I'm just gonna ask you some probability questions, okay? So what is the probability that a randomly selected pregnancy lasts less than 260 days? Okay, so this is exactly like the Chips Ahoy problem, basically, okay? It's just instead of chips in a bag, we're talking about length of pregnancies. But they're all normally distributed, mean, standard deviation, and then I'm gonna ask you some probability, okay? So you're gonna start the same exact way, okay? Step 1, you're gonna define the variable, okay? So if I select a pregnancy, do I know exactly how long it's gonna last before I, you know, get the outcome? No, so it's a random variable. And what you're gonna do next is you're gonna write the probability statement. So I wanna find the probability that that pregnancy, X, lasts less than 260 days, okay? I highly encourage you to do this next. What do I always say step 2 is? Sketch it. Just, you know, I think it's worth it to sketch it. So what I'm doing here is I'm drawing the distribution of the length of human pregnancies, okay? So they're normally distributed, so it follows this bell curve. It's centered at 266, and you want to be less than 260. So I'm going to shade to the left, okay? All right, so to do this in your calculator, you're going to use the command. If you're going to do this on your homework, this is what you need to type next for me to see. Okay, we're going to do this using the calculator, which is the normal CDF. Okay, so everybody grab their calculators, okay? So everybody go to that second function distribution, normal CDF, okay? The first thing you have to put in is the lower value, okay? So look at this curve. You see how it's centered at 266 and I want 260? I want to find the area all the way to the left, okay? All the way to the left. So when you put in something to the left, the lower value, you're going to put some ridiculous number like negative 9999, okay? So all the way on the number line, way to the left of this number, okay? So what's way to the left of 260? Negative 99999. So on your TI-83, what you have to do is you have to put negative 9999, okay? Hit enter over here. Now the upper value is what you're going to stop at. So I want to find all the area up to what number here? Where do I want to stop at? I want to find the area up to 260. Yep. So your upper value is you're going to put 260. On the TI-83, here's where it's a little complicated. You have to press this comma button. So you have to go comma, put in 260. Now, the next thing it asks you is what was the mean, okay? So in your TI-84, it defaults to a standard normal, but let's just put in the mean for the actual length. Because you want to go all the way right up to 260, okay? For the question in the chat. Because you could actually have the length of pregnancy be 259.9 days, 259.99 days. Do you see what I mean? So you want to go literally all the way up to 260. Yeah, I know it's actually less than 260, but the reason we do it this way is because the probability that X is exactly 260 days is so close to 0 that we just put in 260. All right, so the mean was 266 days. So over here, you have to press comma, put in the mean, 266. And then what was the standard deviation for the length of pregnancies? Okay, so then put in 16. You're going to go down to paste. So over here, you just have to hit comma 16. So when you hit paste, you see this. So over here, all you have to do is close the parentheses. And now everybody hit enter on their calculator. How many people got this? The most common way you got an error was you put a subtraction sign here instead of using the negative sign if you're getting an error. But this right here is the answer. Okay, so it's 0.3538. So I'm going to put that in. So here's what we did. We did normal CDF, negative 9999 up to 260. Then I put in the mean 266, the standard deviation, and it was 0.3538. Yep, I'm still a little confused about. So here's what's going on, why you have to put that number in. So this number line actually goes on forever, okay? So obviously, like a human pregnancy can't last less than, you know, how many ever days, okay, whatever it is. So what you do is you just put in a ridiculous number to capture all the way to the tail, okay? So whenever you have a lower tail here, you're gonna put in negative 99999. And then you're going to see in a second when we do the upper tail, we're going to put in the upper tail as 99999. Does that help kind of clear it up, Mary Kate? Okay. Let me ask in the chat here, was this, yeah, go on ahead, Liliana. You can just jump in. You don't have to raise your hand. You can just jump in.
The number 999.49. Where do you take that number from? Or you just?
It's just the number that I picked to do these problems. You could put in, you could actually like even put in 0 and you'll notice you get basically the same thing. You notice you get like the same exact number here. Do you see on the calculator?
Yeah.
So you just want to pick a number that's so far away from this number here that it's going to capture all the area possible. Okay. So what I'm telling you guys in this class is always use negative 99999, or you'll see in the next example use positive 99999, just as a way to know how to do this.
Okay, but if you pick to choose, if you choose a 0, will be -0 on the left side and +0 on the right side?
You can't pick 0 on the right side, right? Because you have to pick a number that's to the right of 266. Like,
so if I have to pick a 0, that should be only on the left side?
Yeah, because like think of a number line, right? Like think of this as a number line, right?
Mm-hmm.
Like here's 0, here's 260, 266. Like, yes, so every question you shade to the left, you're going to use this number as the lower every time. Okay. So just bear with me, just use negative 99999 whenever you're going to shade to the left. Okay. All right, now how about can I move on and do this next one to do a problem to the right? Okay. All right, so what is the probability that a randomly selected pregnancy lasts more? Now I'm asking you, what's the probability that that pregnancy lasts more than 272 days? Okay. Actually, let's change this. I'm sorry, because we're going to end up getting the same thing. Let's change this to be 280 days. Okay. All right. I'm changing it to 280 days. All right. Sorry about that. All right. So now here's the thing. I wrote the probability statement. What do I say always helps me solve this? All right. Let's do the sketch. Okay. So it's centered at 266. And I want to be greater, I said, than 280 now. So I'm going to shade now to the right. Okay. So I'm going to use my calculator here, which is normal CDF. Okay. You shouldn't get a negative answer. So let's look at this, right? Okay. Grab your trusty calculators. Okay. I got to reset this. Okay. So everybody hit second function distribution, go to normal CDF. All right, here's why I like the drawing. All right, the lower value represents the area, what number you start at to find the area. Okay, so I want to start at what number here and begin finding the area. I want to start at 280. So that's my lower. Like my lower is my starting. Okay, so over here I'm going to put 280. Now I got to find my upper. Okay, so now do you know how it goes all the way to the right? Okay, whenever you have a tail area to the right, you're just going to put in 9999. Okay, so over here you're going to go comma 9999. So then the mean is still going to be 266, and the standard deviation is still going to be 16. So over here you have to hit comma 266 comma 16. So hit enter. How many people got this answer?
I did.
Okay. So so the answer is 0.1908 when I round it to 4 decimal places. So my normal CDF, I started at 280, a tail area to the right, I want to go all the way out to 9999. It's okay, don't worry about caps being broken. 266 comma 16, and it was 0.1908. Okay.
Professor, I got confused why you started from 280 and on the previous one you started from the negative 999.
Yep. So here's the thing. The reason I started at 280 is like the lower value is your starting. Okay, so I want to start finding the red shaded area at 280. Okay, so the red tail area goes all the way to the right. So whenever you have a tail area to the right, you're going to put a positive 99999. Okay. Over here, do you see how the area is to the left here? So when you have an area to the left, the lower is going to be negative 99999, and the upper is going to be where you're stopping your area. Does that help a little? We're going to do another example so you'll get to practice this more. Yes, no, doesn't help, helps? Okay. All right, let's try this last one. What is the probability a randomly selected pregnancy lasts between 260 and 280 days? So it's the probability that it lasts between 260 and 280 days. Okay, so now it's between. So I'm going to sketch the drawing. Yes, that's correct. So it's going to be 266, and I want to find between 260 and 280. That is correct in the chat, Leonardo. But let me walk through this, okay? So I want to find this red shaded area. So you're always going to use the normal CDF command, okay? So when you want to find something between, the lower is where you started, okay? So I'm starting at 260, and the upper is where you're ending. Well, I want to stop finding the area at 280. And then the mean is still 266, and the standard deviation is still 16. So I'm just going to do this on the TI-83 here. So it's normal CDF. I'm going to start at 260. I want to go all the way to 280. And then the mean was 266, and the standard deviation was 16. Close the parentheses. Yep, and you get 0.4554 when I round it there. Okay. So it's hard for me to see, but like, does this seem easier or not easier than the way we were doing it? So I think that, wait, yeah. So I think what's confusing is like, when do I use the negative 999 and when do I use the 999, okay? So let me just reiterate that, okay? Whenever you have an area to the left, the lower is gonna be negative 999, and then your upper is gonna be where you wanna go up to. I wanna go up to 260. When you have an area to the right, like more than, your lower is gonna be that value, that starting value, and you're gonna put in positive 999. When you wanna find the area between two numbers, your lower is gonna be the first number and the upper is gonna be the second number. That's it. All right, let's do one more of these, okay? And then we'll take our break. All right, sound okay? And listen, if you don't like the calculator, you're more than welcome to do it by hand. You can totally do it by hand, but I just think that the calculator with practice is a lot easier. Okay, here's the next question. A packing plant fills bags with cement. Okay, they just have cement bags. And the weight of the bags of cement follow a normal distribution. So I'm telling you, normal distribution. I give you the mean. Okay. So mean mu is equal to 50. And the standard deviation is 2 kilograms. okay? So here's what you're gonna do. These bags are coming off the assembly line. You're just gonna select a bag at random. So that's gonna be a random variable. We're gonna let X be the weight of that randomly selected bag. All right, so now I've got the same basic 3 questions here, okay? First one, what is the probability the bag weighs less than 49.5 kilograms? So it's probability that X is less than 49.5. All right, I know it seems silly, and unfortunately you're gonna hear me say this a lot over the next week of class, but what helps? Yeah, so what I'm gonna do is I'm gonna draw the distribution of weights of bags of cement. And it follows a normal distribution, which is centered at 50. And I want to be less than 49.5. Okay, so am I going to shade to the left or to the right? Yeah. Okay, so it's normal CDF. The first thing you have to put in is the lower. Okay, so I said, remember what I said for a tail area to the left. Okay, what number are you going to put into the left here?
The negative 999.
Negative 9999. Yep. Awesome. And then the next thing you need is the upper. Well, I'm going to stop at what number here?
49.5.
Yep. And then the next thing you put in is the mean, which was 50. And then the next thing you put in is the standard deviation, which was 2. So normal CDF, negative 9999, comma 49.5. If you have the TI-84, it's so much easier. So I'm just focusing on the TI-83 here, comma 2. And I'll just do it on this one here so you can see. Normal CDF, negative 99999, 49.5, 52. How many people got this answer? 0.4013 when I round it.
Yeah, I did.
Awesome. So you saw me do another one with the calculator. Kind of making sense? What do you guys think? Yay, nay in the chat. Better, worse, making sense? Nobody's saying anything. Okay, I got one makes sense. Okay. I think, Emmanuel, you said it was confusing before, but do you not see a second example? Does it help?
Yep.
Okay, good, good.
My calculator is saying error.
So the most common error, do you have a TI-83?
84.
You have a TI-84? The most common error is when you're putting in the negative number, are you using the subtraction sign or the negative here? You have to use the negative sign here.
Where is that?
Do you see on the screen, I have my mouse hovering over it. It's next to the enter key.
Oh, yes.
That's probably, were you using the subtraction sign?
Yes, I was.
That's if you fix that, that'll be your error will go
But I
away.
was using it previously and it didn't say anything about error.
I don't know. Let's try this next one and see what happens, okay?
I got it now.
Okay, good.
Thank you.
Yeah, what is the probability? So here's the thing. If you do this by hand, your answers will be off just a little bit. The reason is, stop stuttering, Matt. The reason that if you do it by hand, your Oh my God, it's a bad day. The reason your answers by hand will be different is because you're rounding the z-score to 2 decimal places. Your calculator doesn't do that. I've had too much coffee today. So when you go to, like, for example, when you go to take your exam, I'll build in a tolerance on the answers. So like that way, if you do it by hand or you do it by calculator, I'll accept both of them. I'll accept both of them on the homework too. Okay. So yes, if you do it by hand, it should be a little different. All right, let's just quickly go through these next 2. All right, so now it's the probability the bag weighs more than 53 kilograms. So it should be centered at 50. I want to be greater than 53. So now it's an area to the right. So it's normal CDF. When you have an area to the right, what's your lower here? What number am I starting at? And thank you. And then when you have this area that shoots off to the right, your upper is going to be 9999. You're going to have mean 50, standard deviation of 2. So normal CDF, 53, comma 9999, comma 50, comma 2. How many people got this? 0.0668. Okay. Great. Now the last question, what is the probability it weighs between 49 and 53? So you're at 50, 49, 53. You want to be between those 2 numbers? So this one here, normal CDF. No, we cannot do a break, unfortunately. My wife texted me and says she needs me to hold the kids so she can take a bathroom break. Sorry about that. Normal CDF, what's my lower here? Yep, so it's 49. What's my upper? Yep, and then the mean stays the same, 50, standard deviation of 2. I'll do it in the TI-84 this time. So second function distribution, normal CDF, you're going 49 to 53, mean of 50, standard deviation of 2. How many people got this? 0.6247 when I rounded it.
I did.
Okay, so you are more than welcome. Okay, and actually I encourage this on your homework to use the calculator. If you do that, you just need, this is what I need to see, okay? I need to see the probability statement, type out what you put into your calculator, and then the answer, okay? So I know there was a lot of like, oh, this is a little rough at the beginning, but now that you've seen me do 2 examples, easy. I think you guys can knock this out of the park on the exam. Yep, way easier, way easier. All right, so let's take a 10-minute break. Let's be back.
Could you go back so I can take a picture of the last slide?
Yep. I also, I also post these like right after class too, but you're more than welcome to. You know, like just as a reminder, if people aren't checking. Let me go back to the classroom real quick. Like under recorded lectures, like right after class, I post the recording and then literally the same PowerPoint with my write-up in it. So, but it is good to write to follow along with me. But if you ever like need it or like, oh shoot, what did Matt exactly type? It's there for you. Okay, so I'll be back at 2:05, everybody.
Can you leave the slide on, Professor, please? The last one. Thank you.
Yep, and then I'll be back at 2:05, everybody. Just can everybody see my video real quick? If you're still in the break, I just thought I'd show you the troublemaker to say hi to everybody.
Cute.
Hello, everybody.
He's cute.
Yeah, he's a good kid. Yeah, this is my class. Say hello.
Hi.
He's what, 4 months? How old are you? 4 months and a couple weeks.
Right.
Yeah. He doesn't get to see screens at all, so he's always like, "What is going on?" All right, buddy. I'm gonna give you back to mommy. I just wanted everyone to say hi, humanize the class a little.
Bye bye.
Okay. All right. All right, everybody, we'll get started in another minute or so. Jocelyn, what do you mean it's always positive? Like the two numbers are always positive? Because it depends on the problem. But like whenever yes, after subtracting, yes, if you're going to do it by hand, you always have to, the answer will always be a positive probability because you can never have a negative probability. Just out of curiosity, you don't like the calculator or you do like the calculator? Yeah, I would highly encourage you to stick with the calculator. So we're going to be doing a lot more of these problems, and I'm actually never going to do them by hand again. I'm only going to use the calculator. So we're going to get like a ton of practice with it. Okay. So I really hope everyone likes using the calculator. All right. Before I get started again, does anybody have any final questions? Any questions about any of this stuff? You can do the calculator either way. If you do the calculator, if you do it by hand, your numbers should be off a little bit. If your numbers are vastly different, Jocelyn, then you made a mistake doing it by hand. The calculator will always give the right way. So I think that there's people are more likely to make a mistake doing it by hand than with the calculator. Yeah, but if they were very close, which they should be, then you know you did it right. Yep. All right, so just a reminder now, your homework number 4. So even though we don't have class next Tuesday, your homework number 4 that's posted here is due next Tuesday. Like, to be honest, Jocelyn, did you just do the whole homework? Yeah, how long did it take you? 10 minutes? 15 maybe? Yeah. Yeah, like there's no excuse not to get this homework in, okay? It's just to the homeworks are designed just to reiterate the concept. So I highly encourage you after class, please pay attention to the next part of class, okay? But after class, just get the homework, just do it real quick, get it in and out, and then, you know, enjoy watching election night coverage or something. Or don't, I don't know. Next Tuesday is gonna be a rough day, I think. All right, anyways. Everybody okay? Can I get a couple okay to move on in the chat? All right. So I want to move on to our next topic called sampling distributions. And this next topic is the foundation for advanced study of statistics. Now, I'm going to be honest, maybe not. Some of the concepts that I talk about initially are like a little confusing. and I don't know if you guys feel this way, but a lot of times in math, like when you get a theorem, or even in this class, when I introduce a topic, it's kind of like, what the heck is going on? But then after you see an example or two, you're like, oh, okay, that makes sense. You know, like, oh, I see what you were kind of talking about. Like, did you guys feel that way? Like even in the last lecture when I was doing like I feel that that's kind of how a lot of this stuff goes. So for the next 30 minutes or so, 40 minutes, I'm just going to introduce this concept of sampling distributions and just kind of try to soak it in. And then next class, I'll be able to do like examples of it, okay? All right, so I want to talk about today, with the time we have left, the sampling distribution, all right, of the sample mean. Okay, so the sample mean, does anybody remember what notation we used for the sample mean? What we denoted it as? So like the population mean, okay, got the Greek letter mu, it was a parameter. Okay, and then the sample mean, does anybody recognize this notation, X bar? Yeah, okay, so this is what the sample mean is, okay? We call this X bar, and this is a statistic. All right, and so what we want to now talk about is we understand, we've heard the word distribution before, right? Like we've learned about the uniform distribution, we've learned about the normal distribution. So distribution, we understand what that is. The word sampling, like when you take a random sample. So now we're taking random samplings, all right, and talking about the distribution of the sample means from those different samples. Huh, that's like a mouthful. So let me try to like explain the concept to you. Okay, statistics such as X bar are random variables, okay? So statistics, the sample mean is a random variable since their value varies from sample to sample, okay? So X bar is a statistic, but it's also a random variable. Okay, like for example, if let me just give you an example of why it's a random variable. So I teach two sections of statistics, one at 9 in the morning and one at 3, and then this class at 1. Do you guys think that the average height is the same among all the students in my 9 a.m. class as the average height is in this class? Yeah, like no way. It's just the two different classes. Like the averages will be different, okay? And it's like the same for everything. Like the average number of hours of sleep they got last night compared to the average hours of sleep we got in this class last night. Like they're just going to be different, okay? Leonardo, you are such a troll, buddy. You know, there's always one, right? Oh, Leonardo, I don't think that's true, buddy. You are not serious, okay? You're lucky I have a sense of humor, buddy. Okay, we'll move on. All right, so as such, they have a probability distribution associated with them. Okay, so statistics have a probability distribution. Okay, so we've learned about 2 probability distributions in this class. Okay, we've learned about the uniform probability distribution, and we've learned about the normal probability distribution. Okay, so what we want to do in this section right here, this chapter, is we want to focus on the shape. So when I say shape, what I'm talking about is the distribution, the center, and when I talk about the center, I want to talk about the mean, and the spread of the statistic. And so this, the spread is what we call the standard deviation. Okay, of statistics such as a sample mean. All right, is everybody okay if I move on? including the 7'1" Leonardo? Okay. I'm just busting back with you, my friend. All right, so here's the example that we're going to use for this first part, okay, to illustrate this. All right, and I know it seems silly, but I think it's kind of interesting. So I didn't know this until I started researching this lecture. But the weights of pennies minted after 1982, okay, so the weights of pennies are approximately normally distributed. Right, so like this is interesting. Does it make sense that not every penny weighs exactly the same? Right, like because there's a process through minting them, there's going to be a little variation in how much they weigh. Like, does that make sense? Yeah, like not every penny weighs exactly the same. Okay, so we know that the distribution of those weights follows this bell curve. So the average weight, so mu of pennies, is 2.46 grams, and the standard deviation for their weights is 0.02 grams, okay? So here's what I want to do. I want to approximate what we call the sampling distribution of the sample mean, okay, which is X bar, by obtaining 200 simple random samples of size n is equal to 5 from this population. Okay, so what the heck is all of this mean? All right, what I'm going to do is I'm going to sample 5 pennies. I'm going to compute their average weight. Then I'm going to do this again. I'm going to sample another 5 pennies. And then I'm going to compute X bar for that sample. And how many times did I say that I'm going to do this? What does it say here? How many simple random samples am I going to obtain? Okay, I'm going to do this 200 times, okay? So what I'm going to be looking at, just so we're clear here, is I'm going to be looking at 200 X bars, okay? 200 sample means. All right, like let me show you what the first time is everybody okay if I move on from this? Okay, so I've got 200 X bars. Okay, so like what you're going to notice on the following slide here, okay, these are the 200 sample means that I have. Okay, so for example, the first time I did this, okay, the first time I sampled 5 pennies, I had the following data, okay, and look at what their X bar was. Okay, so for this sample, this is the sample mean. Okay, but just recall the population mean was 2.46. Okay, that's what the real average is. Okay. Okay, is my sample mean different than the population mean? Yeah, right? Like, so just note here. The sample mean, X bar, is different than the population mean mu. And like, let me ask you this question. Does that make sense? Like if I'm just taking a sample of just 5 pennies, would it be okay if I got the sample mean to be different than the real population mean? Like, is that okay? Would that happen, do you think? Yeah, like it's just 5 pennies. Of course, like their average is going to be a little different. Like it's just, you know, it's just a random sample of 5 things. Like that's perfectly okay. All right. Perfectly normal. So like, here's the full data set. Okay, so these are my 200, okay, X bars. So what I want to do now is I want to investigate the distribution of these 200 X bars. So next, what we want to look at how the X bars are distributed. Okay. And this is really amazing. What statisticians and mathematicians have discovered, okay? Okay, so if you look at the mean of these 200 sample means, okay? So the mean of the 200 sample means is exactly mu, okay? So the average of the averages so the average of the X bars is the population mean. So here's what's going on with that. What that means is like, all right, well, I took a random sample and I got a mean that's different from the population mean. Okay, yeah, whatever. I took another sample and another and another and another and another. And if I took the average of the averages, it turned out to be the same thing as the population mean. Wow, that's crazy, okay? The next thing I noticed that's a little weird, okay, is if I were to calculate the standard deviation of all these, okay, the standard deviation of the sample means is actually turns out to be this number, 0.0086, which was smaller than the standard deviation for the population. So just recall the population standard deviation was 0.02. This is 0.0086. So it's different, okay? So the standard deviation for the distribution of the X bars is different from the population mean. Or from the population standard deviation. So what I do in the next slide here is I took all these 200 sample means and I constructed a histogram of them. Okay, is everybody okay if I go to the histogram and talk about it? Got a couple here. All right. Check this out. Wow. What does this histogram look like? What type of shape? It's not perfect, but what does it roughly look like? Low, high, 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 low, 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 low. Yeah, thank you. Right in the chat. Looks like the normal curve. All right. This right here looks like the normal bell curve. And it looks like that if you were to superimpose the bell curve, the high point of the bell curve, it's centered at the mu, 2.46. It's centered at the population mean, okay? So this right here is the distribution of the sample means. And it looks like this distribution is approximately normally distributed. Which is crazy, because this is kind of what the crux of it is. It's like, all right, look, I realize that when I take a random sample, the average of that random sample is not going to be exactly the population mean. Sometimes it's going to be way lower than it. Sometimes the sample mean is going to be way higher than it. Okay. Most of the time when I take a sample mean, it's going to be closer to the real value. And as a result of that, you get this, whoosh, this nice looking bell curve. Okay. So I guess my question for you is this in the chat. Look, whenever I take a sample mean, I don't expect it to be exactly equal to the population mean. But if I were to repeat this experiment over and over and over and over again, all right, and I looked at the distribution of these sample means, the result would be a bell curve. Does that kind of make sense? Like most of the time you're going to be really close to the real value. Sometimes you'll be way above it. Sometimes you'll be way below it, but not as often as you'll be close to the real value. Kind of makes sense? All right, let me expand on this a little bit. So this was only sample sizes of 5, okay? So now what role does n, the sample size, play in the standard deviation of the distribution of the sample mean? Okay, so the real question here is like, what happens when you increase the sample size? Like, do you notice what I said here is that the sample size of each of these sample means was only 5? Like, what happens if I did 20 instead of 5? Okay. Let me ask you this, okay? And this is kind of like the theory behind it is, if you're taking a random sample, is a larger sample size better or worse than a smaller sample size? Larger sample size better or worse? Yes, yep. Okay, so now the question is like, what do you mean by better, okay? Better means is that your statistics are more accurate. Okay, they're more accurate. Like, for example, you know, next week we have the presidential election, right? Like, so if you wanted to do a political poll, it would be better to call 1,500 people than it would be to call 500 people, right? So like, the larger the sample size, the better the results is, that means it's more accurate. So if things are more accurate, what does that mean in terms of the standard deviation? It means that the standard deviation, the variance, should get smaller. All right, is everybody okay if I go to the next slide? I can't tell if people have zoned out because now we're into theory instead of examples. I'm going to go to the next slide. All right. So here's what happens, okay? As the sample size increases, the standard deviation of the sample mean decreases, okay? Which is exactly what I have here, okay? The standard deviation gets smaller, okay? So here's what I want to do. I want to redo the same experiment, okay? So approximate the sampling distribution of the sample mean by obtaining 200 simple random samples of now size 20 instead of size 5. So previously, did 200 samples of size n is equal to 5. Now we're repeating the experiment but with sample size of 20. Okay, so now my sample means are not from samples of size 5, but from samples of size 20. So this right here is what the histogram looks like when I increase the sample size. Okay, what does this histogram look like? Yeah. Okay. Does it look like a much better normal distribution? Like, does it look a lot more cleaner, like tighter than the one before? Like, let me go back. This was the histogram for sample size 5. You know, it's like, yeah, it kind of looks like a normal distribution, right? But like this one like looks like a normal distribution. Okay, like it looks better. Okay. It turns out that this histogram is also centered at the mean. Okay, so the average of these averages still stayed the same. It was still 2.46. But if you were to calculate the standard deviation of this, it got much smaller. Okay. So as expected, when we increase the sample size, there's less variability in the distribution. And we saw as the sample size increased, boom, right? I got this much cleaner normal distribution. It looks so much better. All right, is everybody okay if I move on? I got one yes. Okay. All right, so finally, what can we conclude from this? Okay, and this is probably one of the most important slides from today. Okay. All right, and this is talking about the mean and standard deviation of the sampling distribution of X bar. Okay, and it goes like this. Suppose a simple random sample of size n, okay, like we did in the previous examples of size 5 or size 20, is drawn from a large population with known mean mu and standard deviation sigma, okay? The sampling distribution of that X bar, so the sampling distribution of the sample means, will have a mean, which we denote as mu sub X bar. Okay, so the mean, we denote, you'll see me write as mu sub X bar. So it's the average of the averages, okay? That's gonna be equal to whatever the population mean is. Okay, and the standard deviation, which I'm going to actually refer to as the standard error instead, we denote as sigma X bar. And all you do, it's like one of the easiest formulas in the class, is you take the population standard deviation and you divide by the square root of n. Okay. Which is why we notice you're dividing by the square root of n, that as you increase the sample size, the standard deviation got smaller than it was here. Okay, that's because, you know, the sample size here was 5 and here it was 20, so the standard deviation decreased. All right, so now we know what the mean and standard deviation is, okay, for a sampling distribution of X bar. All right, let me ask you this question. I'm going to pause for a second. Are people kind of like, this is a little confusing, or this is a little weird? You can be honest. Yep, totally, and I get it. There's a huge question mark in the brain. I totally get it. But let me ask you this, and this is why I always say, stay with me here. Like, do you notice, again, like, as I explain a concept and then once I do a couple examples, it makes sense? You guys agree with that? Yep, just got to bear with me on it. Okay, like I'm just trying to lay some foundation, and then once we do some examples, boom, it's going to make much more sense. Okay. So some key important things here. All right, if the random variable X, okay, and like what X was in the previous example was weights of pennies, okay? If pennies are normally distributed, weights of pennies are normally distributed, then the distribution of the sample mean will be normally distributed. Okay, so if original variable is normally distributed, like X was the weights of pennies, weight of a penny, then the distribution of X bar is normally distributed. So X bar was like, even in the first example, it was the sample mean weight of a random sample of 5 pennies. Which I think makes sense. Like, okay, if the original variable is normally distributed, well, then the average of those of that random variable should also be normally distributed. All right, everybody okay if I go to the next slide? Okay. So the mean of the sampling distribution is equal to the mean of the parent population, always, 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 okay? So the average of the averages is the average. It's always equal to that. And the standard deviation of the sample means is always equal to the population standard deviation divided by the square root of n, no matter what, okay? But we have the most important theorem in the class, okay? Like if I say, you know, if you want to remember one thing from this class, it's to remember this, okay? And it's what's called the central limit theorem. Especially if you ever go on and take another advanced statistics class, or you go to graduate school and you take a methods course, the central limit theorem will be like the thing that comes up the most, okay? And it says the following: the shape of the distribution of the sample mean becomes approximately normally distributed as the sample size n increases, regardless of the shape of the population. So if we sample from a non-normal population, as n continues to get larger and larger and larger, the sampling distribution of that sample mean becomes a normal distribution. And it actually happens as long as the sample size is greater than or equal to 30. As long as that happens, the sampling distribution of your sample means will be normally distributed. Okay. I do want to just get through one last slide here and explain this for you, okay? So what do I mean by a non-normal population versus, and then this distribution of the sample means will be normal? Like, what the heck am I talking about, okay? So is everybody okay if I just go to the next slide and get through this one last example? Okay. And this last example is going to explain this central limit theorem to you, okay? What sporting event just ended a couple days ago? What big sporting event did we have? Anybody know? The World? Yeah, the World. Who won the World Series? Did anybody know? It stunk. I was rooting for the other team. It was the Dodgers versus the Tampa Bay Rays, and the Dodgers won. Okay. So I want to talk about baseball players for a second. Okay. I want to talk about baseball player salaries. Okay. So if you bear with me on this, okay. Let me give you the average baseball player salary. The average baseball player, or the average salary, okay, and MLB is roughly $4.4 million a year. Is that pretty good? Is that pretty good money? What do you guys think? I just want to see who's still paying attention in the chat. Do baseball players make pretty good money on average? Oh, come on. I'd play baseball for like 1 year and then retire. Okay, that's pretty good money. All right. The highest paid baseball player last year, I think, made $37.5 million a year. Okay, I'm just curious, does anybody know who the highest paid baseball player is? His name is Mike Trout. Does anybody, has anyone ever heard of Mike Trout before? Yeah, Danielle's got it. He's an outfielder for the Los Angeles Angels. Okay, he's like the best player in baseball. Okay, he's awesome. Okay. So then there's also a league minimum salary. And believe me, there's a reason I'm doing all this, okay? So if the league minimum is roughly $550,000 a year, okay? All right, so if you're just a random ball player and you're on the league minimum, you make over $500,000 a year. Is that still pretty good money? Yes, okay, like it's more than I make, okay? It's definitely good money. So let me talk about the distribution of baseball player salaries. Why did you choose to be a baseball player? I mean, if I could have been, I would have been. I'll tell you why I'm not a baseball player as a sidebar. I tried out for my varsity team in high school, but I couldn't hit a 70-mile-an-hour pitch. I just couldn't do it. So I couldn't play. I couldn't play high school. I couldn't even make it at high school ball. Okay. So I want to show you what the distribution of baseball player salaries look like. Okay. Here's the league minimum, okay, at $550,000. Okay. Here's the league average, which is 4.4 million. And way over here is how much Mike Trout makes, okay, which is 37.5 million. Do you guys think most baseball players make more or less than the average salary? Okay. So think about the average baseball player. Do you think the average baseball player makes more or less than 4.4 million? Well, I'll help you out here. The average baseball player makes way less than 4.4 million. The majority of baseball players make less than the average, and the average is skewed because there's a few players that make a ton of money, okay? Like Mike Trout makes $37.5 million a year. The second highest paid player in baseball is Garrett Cole. He's a pitcher for the Yankees. He makes $36 million a year, but not a lot of players make that. The vast majority make less than the average, okay? So this is a right skewed distribution. All right, so I'm gonna do an experiment here. I'm gonna sample 30 baseball players and record their average and record X bar, which is their average salary. Okay. So the first time I do it, sample 1, okay? X bar comes out to be $5 million, okay? Is that a little bit different than the actual mean? Like when I sampled 30 players, I got a sample mean of 5 million. Yeah, that's a little bit higher than the population mean of 4.4. If I do this again, if I do it another time, sample 2, like I sample another 30 baseball players, X bar gets to be 4.1 million. okay? If I did this 100 times, let's say the last sample average ended up being 4.4 million exactly. Okay, so I have 100 sample means. What would the distribution of these sample means look like? Well, it turns out it's really amazing. Here's the average baseball player salary, which is 4.4 million. The first sample, sample 100, or sample 1, ended up being 5 million. It's over here. Sample 2 ended up being 4.1 million. That's over here. If I were to show you what all 100 samples looked like, you would see this. Each of these dots is supposed to represent a sample. What does it look like on drawing? It would look like a normal distribution. That's okay. No, yeah, I meant what you're totally fine with what you said. Just like the shape of it would be a normal distribution. So even though I sampled from a non-normal distribution that was right skewed, like baseball player salaries, okay? If I did a sample size of at least 30, okay, which is what the central limit theorem says, as long as the sample size is greater than or equal to 30, the distribution of those sample means would be normally distributed. And it looks like the mean here of this, the average of these averages, was still equal to the population mean, which is crazy. All right, I know this was a lot, but I'm gonna stop here, okay? The big takeaways from this last 50 minutes of class, or last 40 minutes of class, okay, is that the distribution of X bar is gonna be normally distributed if either the original variable is normally distributed, and if the original variable is not normally distributed, as long as the sample size is greater than or equal to 30. Okay. Next class, what I'm gonna do is we're gonna work a bunch of examples of this, and I promise you, you'll see how we use this and it'll make a little bit more sense. All right, what a class. I'm gonna stop the recording real quick.